So we'll move to the last tutorial of the session. Hari, I think, will be introducing the speakers.
Sure. I believe you can see my screen. Hi all. Thanks for staying with us until the last talk. The last talk will be from X-ScaleSolutions. The topic will be accelerating HPC applications with MVAPICH2 DPU, and there will be some live demos with this. There will be 3 presenters in this talk, led by Dr. Donglai Dai, who's the chief engineer at X-ScaleSolutions and leads the company's R&D team. His current work focuses on developing scalable and efficient communication libraries, as well as checkpoint and restart libraries and performance analysis tools for distributed and parallel HPC and DL applications. He has 20 years of industry experience in engineering management and development of computer systems. He's a graduate of our lab. Richmond Lee is a software engineer at X-ScaleSolutions, and his responsibilities are centered around building the testing infrastructure and development of the MVAPICH2 DPU project. Nick is also a software engineer at X-ScaleSolutions, and he's also a master's student at our lab at The Ohio State University, and he's working on designing and developing the MVAPICH2 DPU software stack. So with that, let me hand it over to the folks at X-ScaleSolutions. Donglai, would you like to share your screen? Donglai, Nick, Richmond, are you there?
Yep, I'm here. Can you guys hear me?
Yes. Okay. I think Donglai is just starting to screen share. I can see your screen, Donglai.
Can you hear me now?
Yes.
Okay. Okay. I will start. Okay. Thank you for attending this tutorial and the live demo. And today we're going to show how do we use the DPU, MVAPICH2 DPU library to do for offloading, using offloading to accelerate HPC applications. And this is a product from X-ScaleSolutions. So as we know that MPI is the most popular communication libraries used in HPC as well as AI applications in high-end computing. And as new hardware and software come into place these days, and so there's new requirement as well as challenges for MPI to take advantage of this new technologies. As we know that for the basic requirement for MPI, we try to achieve low latency, high bandwidth, and with minimum contention on host CPU resource, so that we can achieve as much of a progress from overall compute application perspective. Okay, and we also try to achieve high overlap between communication and computation, so that the end user will see the overall execution time get improved. So one of the things for CPU-based non-blocking communication is that if you have a progress thread to help you to do the communication, is its contention for the CPU resource from the take away that kind of a resource from the end user's application computation. So how do we develop and develop the MPI library to take advantage of this attraction, new attraction on the network offloading capabilities, and to improve the communication efficiency? Okay, that's the challenge we take up. To this end, we are looking at a particular, especially for this library as well as for this demo, we're looking at a particular version of the DPU, which is from NVIDIA BlueField-2. Okay, and here we show that on the right, the overall high-level picture of how a node looked like. As you can see on the top, it's the server, the most popular ones. Okay, a bunch of CPU cores with memory attached to it. And then on the lower part is the DPU part. And for this particular DPU unit, it actually integrated the Connect X6 network adapter, as well as an array of ARM cores with its own attached memory. The connected 6 has a network bandwidth of 200 gigabits per second in infinite band. Okay, and the ARM cores are 64 bits ARM V8, A72 core. That's the model, and it's clocked at 2.7 gigahertz each. That's the latest version from NVIDIA. And attached memory to the ARM core is 16 gigabytes. So how to restructure or redesign the MPI library to take advantage of this DPU is what we try to show. Okay, and that's what our library has been achieving. And this is the latest release. We just released it yesterday. Okay, and this library, MVAPICH2 DPU library, version 2021.8, and it's totally compatible with the open source MVAPICH2 2.3.6. That's the latest open source version available on the internet, and it supports all features of this library. Okay, basically means this the DPU library is compatible to the open source, and the DPU library has we invented new framework to do the offloading, especially for non-blocking collectives. And currently we already support the 3 of them. One is all to all, another one is all gather, the last one is broadcast. And as we move on, we'll add more and more under the same framework for the offloading. So, and as we have, what we have achieved in this release is we can see significant increase of up to 100% overlap of communication and computation. And the communication used can be any of the supported non-collectives, non-blocking collectives. And we actually see the end user application, the scientific application, and see the significant impact and improvement because this improvement using this library can achieve using the offloading capabilities on the DPU. And this release, the latest release, is available from our company X-ScaleSolutions. If you are interested, please send a note to the contact us at xscalesolutions.com and get a trial license. Okay. And in today's demo, here is the system of configurations we use just for people to get a sense how we are evaluating in comparison. So we're going to run HPC-Al cluster, which has 32 Xeon nodes, Xeon hosts, and each of them connected to one DPU. So we have also 32 DPU units. And overall, in the entire cluster, it has 1K CPU cores, Xeon cores, and 256 ARM cores. So how to use this kind of resource to achieve overall efficient application, okay, to improve the performance on that. And the specific configuration we use is the CPU is the dual core Intel Xeon, okay. The model is E5 2006-97A V4, okay. It's clocked at 2.6 gigahertz. The adapter, which is the BlueField DPU, it has 8 cores clocked at 2.75 gigahertz, which is the latest with 16 gigabytes memory. The software we use is CentOS 8.3, and driver is 5.2, and the firmware version is 2430. And the MPI version we use is our latest release, DPU library. And we're going to use the performance evaluation is OSU micro benchmark version 5.7.1. And for the application we're going to show is P3D FFT, and the version is 2.3. And the demo will contain 4 parts. We'll start with all-to-all, use the OMB, and then continue with application level. Okay, it's a P3D FFT, then followed by IBCAS as well as ICAD. Okay, next, let's Richmond can help us to get started on the demo part.
Yep, sounds good. So let me start sharing my screen. Can you guys see my screen right now?
Yes.
Okay. Sounds good. So let's start with a all-to-all. So before I begin, let me explain the setup of our demo. So right now we're going to be looking at a front end, which will display some data as it comes in through the back end, which is running on HPCAC on Thor, and we have the entire allocation. So the front end will actually initiate a TCP socket connection to the back end. So we will run this with 60 nodes, 32 ppn. And so we hit start, we have a connection, and we will wait for the data to come in. So Donglai, would you like to explain a little bit more?
Let me explain. Yeah. So as we can see here, it's one of the most dense communication, all-to-all. It's a non-blocking all-to-all version. So each of the MPI thread ranks will contribute some of its own data for the overall communication operation. So there's a lot of data exchange going on, as well as many messages within the network. So it's a lot of bandwidth. And so this is what, for some applications, this becomes the bottleneck due to this dense communication pattern. And improving on this, as even we can see, even for the micro benchmark, it takes some to actually see the result. So as later on, when we see the application, you can see actually this is a significant improvement on the micro benchmark actually translate into the end application. Okay, so for this one, you can see that as it will come out, it's actually quite sustainable. It's based on different message range, as well as for this particular configurations. And by the way, because a demo, we only see one configuration, but as we test it, we test all kinds of configurations for different. And they all say sustainable performance, and it's quite similar. And so that is something, it's very convincing that this is something we can provide for a wider user to use. Once you have access to a DPU like NVIDIA DPU. Okay, it should come up soon. And as Richmond explained, so the 3 windows will show the overall execution time as well as overlap and the pure communication time. So when we design this, of course, the overall goal is to help the overall execution. And our approach is trying to achieve as much as overlap possible to achieve that. Okay. Of course, we try to, the end goal is to reduce the overall execution time. from the application perspective. And as you can see that the overall improvement here for this live data is about between 15 and 20, 21 or 22%. And for pure communication, and the improvement is about 30 or 40%. And during this communication, operations will achieve 100% overlap, which actually is quite noticeable. Okay. So next, we are going to see from the P3D application perspective, how this improvement a dense non-collective communication like I-all-to-all is going to be transferred to translate to the end applications perspective. And this one we're running P3D FFT, which is one of the most popular computation core in many HP and HPC computation applications. And here we only show one window, which is looking at the overall execution time. And as we can see that we want to not only looking at a single point, rather than different data size, input size, and see how sustainable or how stable the improvement is. And we already have the first data points here, and which is the input for P3D is a dimension, a 3D matrix. Okay, so it's for each of the dimension we start with 1K. So it's 1K by 1K by 1K, the data input size. Okay, and for our task here, demo here, we're going to increase one dimension, double that index size, one dimension at a time. We can see how this application overall execution time changes. And for the data we can show here now, we already see that the improvement actually is quite sustainable. It's about 22% for this one, very stable, even though the data size is changing. Okay, and for this two particular one is the second one is increase double the last, if we call it a Z, double that size from 1K to 2K. Now this third set is we increase the second dimension from 1K to 2K. And again, the improvement is about 21%. So as you can see, once we see the last one, we'll see that actually this is very stable, the improvement on the overall execution time for P3D FFT on this cluster. And the red bar is for the MVAPICH2, the open source version. And the green bar is for the one with our library with DPU offloading enabled. So the last one is data size get larger, so the overall computation time, execution, overall the overall execution time gets longer. And where this one is the maximum we can run with this application. I mean, from number of nodes as well as number of cores. Okay, so it's in total it's 1,000 MPI ranks, using all the CPU cores on all nodes. Okay, and the last one, as you can see, it's 21% improvement on the overall execution time. Okay, the next we will show that the performance evaluation on IBcast. Okay, and again we use a microbench OMB macro benchmark to show the evaluation result. And we're using for time interest, we're not using the maximum possible, but as we can mention before, actually the performance are similar. Actually, for this library per se, as a system get larger, the margin normally, improved margin normally get increased. But even for this reasonable size, we can already see the noticeable improvement on the performance. And the interest for non-blocking broadcast is, broadcast actually is the most fundamental collectives for most fundamental communication pattern for all collectives. Okay, so any other collectives, it's some variation or enhancement, or sometimes multiple operations based on the bcast. So for this one, it's not dense collectives, but we still see significant improvement. So this actually proves the basics of our approach. It's very, very solid. So, but as you can see, the overlap may not be improved that much. It's actually what happens is, as we focused on to improve the overlap using the DPU for overlap, and we find new ways to balance the computation and the communication. We try to, the overall goal is to reduce the overall execution time from the benchmark as well as for the application. So that's sometimes we take the, especially with the DPU, we take some schemes so that it's actually achieve the end goal rather than to maintain that the host as well as the DPU with or without the DPU capability enabled to be, the code is identical, okay? So each time we try to achieve the overall goal, we sometimes optimize to optimization take advantage of the best for host as well as the DPU. So the overlap may change somewhat. Okay, next. And this is the last part of our demo. And it shows our capabilities to for the offloading iGather. Okay, and we are going to see that actually it's similar performance improvement on the overall execution time as well. Okay, so iGather it's more dense than the IBcast. So it's take a little bit longer, but it should take less time than iAuto. So just a little bit it will show up. And again, as we can see that the improvement on the pure communication time is going to translate to overall execution time. And as we continue to, because right now is we first focusing on the DPU offloading, okay? And as we move, as like we have done in the multicast, we find new opportunities to improve, take advantage both host as well as DPU resource to achieve overall the best result for overall execution. So that when we have done something for the IBcast, and this one we were also continue to improve on the iGather as well, especially on the host offload, host version of it. Okay, and as you can see, this there is also significant performance improvement for this particular iGather operation as well, and the percentage is something like about 40 to 50% improvement. 40%, I should say, 40%. Okay, so that concludes our demo, and next, I will just conclude with a few slides, and then we're open for a question and answer. Let me share my screen. Okay, as we have seen that's what our current release features are, the highlight of the features, okay, and what the impact on the performance. And the next release, upcoming ones, we're going to support, have special support for using the DPU offloading for to accelerate DL training. And we are going to support distributed CPU-based DL training with the DPU, with novel designs. And we internally, our evaluation already show that it's improved up to 15% overall execution time with the offloading enabled. Okay, it for this DL, we're supporting the PyTorch as well as Torch version, and that's particular ones we have used for evaluation. And the result actually is published. The design is based on whatever this research is. The research is done, is already published very recently, actually a week ago, in Hot Interconnect. Okay, and interesting. Someone, if interested to look into more details, can look up can check out there. Okay, so this feature will be available in our next release of MVAPICH2 DPU library. Okay, and we will have more versions to continue more support for different non-collectives, as well as other collectives, as well as new features to be added to support the more DL as well as HPC applications. Okay, now that concludes our presentation for the demo. We are open for questions if there is any. You can ask for data questions as well as for license related stuff if you are interested. Thank you.
Hi, Donglai.
Yes.
We have a question from the audience, Satish Puri, who asks that can a DPU run normal C++ code, or does it require DOCA library for implementation?
Just a moment. Let me see why I'm not seeing. Oh, I may stop sharing. Okay, sorry about that. Okay, can you repeat the question again?
Yeah, maybe Nick might be able to chime in as well, but can a DPU run normal C++ code, or does it require DOCA library for implementation?
Donglai, if I can answer this question.
Okay.
So yeah, the DPU can run, you can think of it as just like a host. So there's two modes, there's separated host mode and then embedded function ownership mode. So we run in separated host mode. And in this case, you can run pretty much anything. Yeah, C++ code, C code. The Doka library is like a convenient site library. I think it comes with some packages that make development easier, but yes, everything should work normally as you would expect on a host.
Yeah, what happens is whatever enabled the host we can run for, C or even Fortran, whatever, as well as the Python. Okay, and we the current ones support like what Nick is explaining. We are going to make sure that whatever can be running on the host, we will support the offloading to make sure that it can run. Now, offloading, enabled offloading itself, it requires some special drivers from NVIDIA, as well as our own library. Okay, it works together.
Are there any other questions from the audience? Okay. So if not, then I think we just exactly we are hitting into 5:30, so we are on schedule.